Thank you very much, and thanks to the organizer for allowing me to be here and to be in your presence. It's really exciting for me. But so this is talking about some objects that were defined by Chermak about 10 years ago that show up in sort of local finite group theory. Specific examples of partial groups that they fill up, and just sort of how associative can they be or can they not be. So I think maybe it's maybe the best way to think about a partial group is simplically, or in fact in terms of symmetric sets. So a symmetric set is a presheaf on category upsilon, and upsilon has the same objects as delta, so bracket in at least 0. But now we don't require maps to be order preserving. We allow any function from m to n. That's a morphism in upsilon. So this is a nice skeleton of the category of finite sets, non-empty finite sets, and all functions. So at the top, you can sort of think about a symmetric set as being a simplicial set together with compatible actions of symmetric group of degree n plus 1 on n simplices for each n. And of course, with the relation that can be satisfied, I think these were written down by Marco Grandis at one point. At any rate, it's interesting what the representable objects are. The standard symmetric, like M simplex. So those are functions from the n simplices in there, functions to bracket m, and this can be identified with the nerve of the chaotic groupoid on n. So one thing that's different, I mean, is that upsilon 2, like the symmetric 2 simplex, that has 3 factorial non-degenerate 2 simplices corresponding to the elements of the symmetric degree 3. So you could sort of write them down and make use of the inverses in this chaotic groupoid. All right, so that brings us to sort of the standard example of a symmetric set, which is we saw in Julie's talk that the nerve of the category is a simplicial set, and if that category happens to be a groupoid, then the nerve inherits structure of the symmetric set. Sort of some maps that you don't have in delta. I'd like to call attention to a couple classes of maps. One are the maybe flip maps from n to n, which just send 0 to n, 1 to n minus 1, or they swap. It swaps those, and so on. And if you take something in the nerve of a groupoid as some composable sequence of n morphisms, then the flips act by inverting that sequence. There are also folds, which are maps from 2n to n, which so 2n has an odd number of things, and n is in the middle. So if you fold along, at the crease given by n in 2n, then you get these fold maps. And what this reaction does is it will give you the concatenation of the inverse of the word with, or the inverse of the sequence with the sequence itself. So there are edge maps that, of course, some of the rho ij from 1 to n that pick out the ijth edge. And of course, if I is less than or equal to j, then those from delta, but if not, then not. For example, rho 3 1 will pick out sort of the inverse of the 1 3, the composite of F2 and F3. So I think in Julie's talk we saw that you know, what is the condition that characterizes the nerve of a category? Well, it's the one Segal, it's this one Segal condition. The one Segal map is a bijection. And actually, Grothendieck wrote this down in FJ3. And at the very same spot, he says, okay, so if you have a symmetric set, or not in this terminology, but if you have a symmetric set, then it's the nerve of a groupoid if you know it. Again, it's one Segal. So we want to weaken the condition that the Segal map be a bijection just slightly, or well, let's call the symmetric set. Oh, and I've been color coded. So for the first maybe half of the slides, if you see some light blue, that's something that comes from delta or some simplicial, and then purple would be like something from something symmetric. So we'll call a symmetric set spiny if the Segal map, sending say an simplex to its spine, is merely injective. And for reasons that become clear a little bit in a minute, we'll call a partial groupoid a spiny symmetric set. A partial group is just a reduced partial groupoid, so a reduced spiny symmetric set, single vertex. So the one thing about partial groupoid or spiny symmetric set is that each n-simplex is uniquely determined by its image under the Segal map, its principal edges. So you might as well write it that way. And then secondly, what this gives you is, in terms of a composition, is it gives you a partially defined composition, which is nevertheless unique, when it does exist. So you take maybe a sequence of potentially composable things, and you ask, oh, does this come from an n-simplex? If it does, it comes from a unique one, and you have its total composite. So you can easily build, examples of non-spiny simplicial sets, symmetric sets, just by taking maybe two n-simplices and gluing them along their spine, and that sort of breaks. Then you'll have two, say in this picture, two simplices that, of course, have the same image, have the same principal ends, so go to the same thing under the Segal map. So, this is not the usual definition. This is not the original definition of a partial group. As I said, Chermak defined partial groups very group theoretically, and identified some important examples that are related to the fusion system of a group at a prime, but not exactly the same. In fact, they contain more information. But according to Chermak, a partial group is a set together with a subset of the free monoid on that set of multipliable words. So you're only allowed to multiply certain words. And if you're given a multipliable word, you have a product map that returns its total composition or total product. And the group bodies, you have some sort of inversion, so an anti-involution from instead of multipliable words to itself, which does act like an inversion. So if a word is multipliable, then if you concatenate the inverse of the word, or the inverse of the word with the word, that's also multipliable, and the product is the identity. But ultimately, I mean, these are ways of, the first, without the inversion, this is sort of, we could boil this down to some sort of simplicial structure, or given an indication of the relevant interpretations on the simplicial side. But this inversion is essentially, I mean, giving you an action of folds. So in Gonzalez, a couple years later, he recognized this was a simplicial thing, and in of course the previous in terminology on the previous slide, identified partial groups as being sort of reduced finite simplicial set plus an inversion, an anti-inversion that acts like inversion. But if you have an inversion on a monoid, there can't be two different inversions on a monoid. Monoid, there's a unique one when it exists, so an inversion is really a property that a monoid can have. It's not extra structure. So this translates into sort of being able to lift your simplicial set to a symmetric set. And then the second thing is that, the second observation that you need is that epsilon is generated by delta and the folds. Right. So I've just given you a very compact picture of the sort of the main result of the paper with Philip, that Chermak partial groups are in fact isomorphic to the category of reduced finite symmetric sets, and that's as a full subcategory. That's a full reflective subcategory of the category of reduced symmetric sets. So there's a nice left adjoint, which may be called spinification, and that's actually, you can actually write down exactly what it does. So I don't have time to describe it here, but one consequence is that it makes it easy to compute colimits in this category, because you can just sort of compute it in symmetric sets and then spinify, and that's the colimit of the diagram, the category of, say, partial groupoids or partial. Yeah, definitely in partial groupoids. Okay, so what are some examples? Yeah, what are some examples of partial groups? Well, I'm just going to stick to partial groups. Anytime you have a group, of course, you have the nerve of that group that considers one object category, so I'm going to call that VG. If you have two groups, you can look at their coproduct in the category of reduced symmetric sets. That turns out to be spiny. But it's a lot easier to, it's a lot nicer. It's just a wedge thumb. It's a lot nicer than the coproduct in the category of groups. It sits inside B of the free product. Much smaller thing. Another interesting example is BCOM-G, so the classifying space for commutativity. So this is a symmetric subset of BG where you remember the n-simplices consisting of elements that pairwise commute with one another. This has been studied sort of from a topological point of view by Hunter and co-authors. But this, I'm thinking of just a mere simplicial or symmetric subset of BG. And just more generally, any symmetric subset of BG, that you want to identify, that's a partial group. So here's an example that hits toward the reason that Chermak defined these objects. So start with an action of a group on a set of Z, and look at any subset of that set, Y. Then you can make a partial symmetric subset of BG, Ly of G, where you keep the n-simplices that act successively on elements of Y. So formally, this is, if you think about like a transporter groupoid for the G set Z, then you have a surjection on the BG, and this is the the image where you cut down to objects in Y. Yeah. So the actual example that comes up is G is finite, acting by conjugation on P subgroups of the group G, and you fix a Segal subgroup, and you keep only the non-trivial P subgroups of that Segal subgroup, and that's your subset Y, and this gives you a specific example of the Chermak locality. Yeah, this is another closely related example, special case is sort of a combinatorial version of a locality where you start out with maybe a finite Coxeter group acting on, I guess at this level generally it doesn't have to be finite, but it will be later, acting on, so you need root system for it, and you cut down to a set of positive roots, and you can ask, you can look at this partial group determined by that partial action of the vowel group on this set of positive roots. So all the examples so far have been symmetric subsets of VG for some G. Here's an example that's not, which comes back to David's question, I think, in the middle of Julie's talk. So one way to build an example that's not a symmetric subset of VG is to build in some non-associativity. And the way you can do that is, well, you take the front two faces of a 3 simplex, back and bottom face, and now glue those along their spines, and you're left with they have different, now the result has 2 different 0-3 edges. One of them corresponds to a composition which is defined, FG then H, and another one corresponds to the other way to associate FG and H. Right? So, and it turns out that's finite. So we did take a colimit. That's fine. That's a partial groupoid. You can reduce it. That's still fine. That gives you a partial group. That's sort of non-associative minimum. Okay, so let's think about some. I just want to think about the 2 Segal conditions, sort of in the context of Julie's example of a Segal partial monoid. So I'm gonna use the words the modifier Segal in front of partial monoid to distinguish that type of partial monoid from something that may be more general. So a Segal partial monoid, remember, is a set with a partial binary operation with this associativity condition sort of built in, right? So M1, M2, M3 is defined, M1, M2, M3 is defined as well. But now suppose we have a Segal partial group. In other words, we have maybe a partially defined operation, but we have inverses for each element of our monoid. Well, in that case, 1 times n is defined, m inverse times m is defined. That's what it would mean for b to have an inverse, and then by 2 you can associate the other way, and you can get that mn is defined. So any 2 products of elements are defined, and so a 2C so a Segal partial group is really just a group. So this condition 2, this associativity condition is forcing, and together with inverse is forcing one Segality. And so this is the first question that Philip asked me: is it partial group 2 Segal? And the answer is well, not unless it's 1 Segal. So so the really only interesting higher Segal conditions for partial groups are the higher than 2 ones. And so I'm going to describe just very roughly, no, I mean, I had a nice description of this paper of Kashi Walden that is the way we sort of think about these higher than two Segal conditions, but it was just too much, and so I cut it. But basically, one sort of motto coming out of this is that that at least lower odd Segal spaces are sheaves for a particular class of covers of bracket n as considered as like a toy manifold. So, and the number of elements in such a cover is k plus 1. And without telling you what these higher Segal conditions are yet, I would like to just mention the a theorem that comes from interpreting Walden paper in this context of say a symmetric set, that two Segal if and only if one Segal is sort of persists higher up. X is upper 2k Segal if and only if it's lower 2k Segal, and only if it's lower 2k minus 1 Segal. But so that's true for any symmetric set, but the sort of concreteness that we have in the setting allows a very down-to-earth description of the Segal condition, which is, well, suppose you have a potentially multipliable word, and you know that at least k plus 1 of the codimension 1 faces of those are defined and are multipliable. And then this potentially multipliable word is multipliable. So it's a very concrete alternative description of a higher Segal set or symmetric set or partial groupoid. Now I mean, that may not speak to you. Let me say a little bit, let me go down the line and say what that's actually saying. We'll start, so I'm just going to, but also the theorem that I put up is just an excuse to only talk about the lower odd higher Segal conditions. So I didn't talk about the other ones. In that case, to check this condition, what you need is a choice for n at least 2k of a sequence of elements of bracket n, which are gap. In other words, adjacent terms in the sequence are, have distance between them at least 2. And this gives you of size k plus 1. This gives you k plus 1 face map. And what I'm saying is, suppose you have potentially multipliable word, well, and you have those faces that are multipliable and the whole thing's multipliable. So for lower 1 Segal, this involves, I didn't tell you, for lower odd, even in the simplicial setting, you need to choose your first term to be 0, the last term to be n. And so the choice is determined for lower 1 Segality. You need to choose 0 and n. And so what we're asking of our partial groupoid is that the D0 and Dn faces being multipliable imply that the word is multipliable, the sequence is multipliable. Yeah, this is equivalent to the, I mean, this is a condition that's equivalent to 1 Segality and more generality than what I'm saying. Okay, so what's lower 3 Segal? Well, then k is equal to 2. We have an extra term of the gap sequence in the middle. Has to be at least 2 less than or equal to n minus 2. And we ask whether if those faces are multipliable, then the whole thing is okay. So then you can keep going. Yeah. I'm sorry that this may be too down to earth for people that would rather see like limit cubes and things like that, but hopefully some flavor comes across, and then we can talk about some more detail in person. But okay, so very concrete. So here's a very simple example. Take BCOM G, any G. So suppose you have a simplex of BG itself. You ask whether it's in BCOM G. Well, you ask whether, suppose you have three faces on that are multipliable. In other words, three faces consisting of elements that pairwise commute. And well, the D0 face gives us that, U2 through Gn commute. The Dn face gives us that G1 through Gn minus 1 commute. And then you do need that extra face that tell you that G1 and Gn commute with one another. And so that implies that G1 through Gn is multipliable. That's a very, very nice, simple example, simple to prove once you know this characterization. Here's got one more sort of maybe class of examples. So I'll come back to this example where we have maybe a combinatorial version of the locality, and I'm reminding you of the definition. So in this partial group, n simplex and BW is multipliable if there's a positive root, A0, such that W1 keeps that positive, W2 keeps that positive, and so on. So that's the partial group. What's the set of one simplices? Well, the only elements of a Coxeter group, finite Coxeter group that doesn't that doesn't take a positive root to some positive root to another one is the longest element. And so the one simplices are just you pluck out the longest element in this of your problem. So you can write down in rank 2 that you can check probably directly that this is lower free Segal, but in fact the way I think about this is in a framework to also talk about higher Segal, sort of higher Segality of any partial group of this type. So this is sort of maybe a pre-theorem, theorem star. Assuming, say, phi is irreducible, it doesn't matter because I think the Segality is sort of additive, appropriately interpreted. And if K is smallest such that this partial group is lower 2K minus 1 Segal, then well, K can be quite large. Yeah. And particular examples, let's say, well, it grows roughly quadratically in the Segal degree, let's say. Nice example, E8, K is 36. And so E8, the Von group of E8, take out the longest element, is 71 Segal, but not 7 Segal. Yeah. So that's sort of interesting. That's all I have. Thank you.
Thank you very much. Question. You know what the Chermak calls the objective partial solution.
Yes.
Let's start clarifying. Does this which makes the partial group 2, 0, 3,
No.
4?
No, it's as bad as, yeah. Even for localities.
Yeah.
They grow pretty fast. Yeah.
So you have this inclusion functor from, like a reduced symmetric set into all symmetric set, and it has a left adjoint by reduction.
Yes.
It's like quoting the zero skeleton out. Does the inclusion functor have some right adjoint as well as some, like, island or some complex kind of construction?
Yeah, yeah, I'm not sure. I'm not sure. Yeah, sometimes if not less than